Hi there, chemistry students. Welcome back to the Formulaic approach channel. In this video, we are going to talk about the hydrogen bonding. All right. This is as relates to organic chemistry. Exactly. So I've begun a series on organic chemistry, which I'll link in the description. So do well to watch the beginning to this point. All right. So now, when hydrogen actually coordinates with other atoms that have high electronegativity value, the hydrogen is bound to take the positive become the positive dipole. Now listen, first you must understand what electronegativity is. I have already explained this, that electronegativity is the capacity of an atom to withdraw electron to itself or accept electron or draw electron density towards itself, okay? So that the higher the electronegativity value of an atom, the higher its capacity to draw electron to itself, and the lower the electronegativity value, the lower the capacity to draw electron, and which means that it will rather give electrons out. Okay, so now we do know that covalent bonds are non-polar bonds, generally speaking, but sometimes it might occur that hydrogen will engage in sometimes we have covalent bond being polar because of the bond between hydrogen and some other atoms that have very high electronegativity values. All right. So since we already know that the compounds, the atoms that we see in organic compounds are carbon, hydrogen, oxygen, nitrogen, fluorine, sometimes chlorine, sometimes sulfur. All right, so I'm going to be using these to explain. All right, this guy has electronegativity value of 2.5. This guy has electronegativity value of 2.1. This guy, according to the Pauling scale now, this guy has electronegativity value of 3.5. This guy has electronegativity value of 3.1. This guy 4.1. This guy 2.8, and this guy 2.4. All right, so you can as well see that, as I've said in the former video, that fluorine is the most electronegative element on the periodic table. So whenever hydrogen engages in covalent bond with fluorine, there is going to be a polarization. Polarization means that there is a distortion, or there is unsymmetrical sharing of the electron cloud between the two atoms that are being coordinated together. So for example, A, for example, is less electronegative and B is more electronegative. What you will see is that rather than have the electrons between them equally shared like this, you are going to find the electron cloud closer to the more electronegative atom, and that is the condition of polarization. So because of this, the guy that is more electronegative, which is the B, our atom B, is going to have slight positive charge and slight negative charge rather, while this guy is going to have a partial positive charge. Now remember, these are partial charges and not formal charges. Partial charges and not formal charges. We use only formal charges when there is an abstraction of the elements of the electron to one atom or to the other atom. But in this case, it is just that they are both engaging in bond, but the bonding is has to do with unequal sharing of the electron cloud between them. Okay, so that is what causes polarization. Now, I was talking about hydrogen bonding now. Hydrogen bonding occurs when you now see hydrogen engage in bonds with other atoms, including oxygen, nitrogen, or fluorine. Exactly. Now, I'm going to be using these two because they are the chief ones that appear, chief atoms that appear in organic compounds. Sometimes we also see fluorine. We are going to talk about with fluorine and chlorine or those halides when we get to effects of polarization. So with this guy, you are going to see that, for example, let's use water in this case. Water is a polar solvent, exactly. Now, the bond that is formed between the hydrogen and oxygen is a covalent bond. So we are going to draw water molecule like this. Okay. So what you will see is that there's going to be a partial negative charge because of the difference in electronegativity value of this guy and this guy. Now, this difference is so high because if you had seen my last video, I said that when the electronegativity value difference is greater than 0.4, then it is already large. And if you compare this and this, if you subtract this from this, you're going to get about 1.4, which is very high. So because of that, there is unequal sharing of the electron cloud. So this guy, it will lead this guy to a slightly positive charge, and so the way we draw it is such that the electrons are moving in this direction, electrons are moving in this direction. Does that make sense? Electron clouds are moving in this direction. So this guy will have a partial positive, this guy will also have a partial positive charge, okay? With this guy being partially negative, negative. Okay, so in water now, hydrogen tends to be, even though it is univalent, it has also been experimentally proven that hydrogen tends to behave like a divalent or bivalent atom. And what does that mean? It means that normally it is univalent, that is, it seeks to coordinate only one atom. But in water, what you see in the crystal structure of water is that hydrogen, so when we form water molecule like this, now this oxygen, because of its high electronegative value, is going to coordinate partially to another hydrogen, which has already coordinated with this hydrogen has coordinated with oxygen, and this guy. So this one will now coordinate with another oxygen, which has coordinated with a hydrogen. This one has coordinated with another hydrogen. This one will seek to coordinate with another oxygen. Does that make sense? Which has coordinated with one hydrogen, and this one also coordinated with one hydrogen and one hydrogen, like this. So you are going to see that continuous repetition of, so this point here, this is the point of hydrogen bond, this is the point of hydrogen bond, this, let me draw the structure correctly. Let me draw it correctly. So we begin with hydrogen bond here. It's going to coordinate with this, and we have hydrogen. So we now have a hydrogen, oxygen, hydrogen. Then this one will coordinate with a hydrogen, oxygen, hydrogen. Then this one will coordinate with another hydrogen, which will coordinate with oxygen, hydrogen, which will coordinate with another hydrogen, okay, which has already coordinated with oxygen and the hydrogen. Okay, take note of the bond angles that I'm putting there using Vespa theory. So, all right, so this is the lattice structure of ice. This is what is seen in the atomic scale or in the lattice structure of ice, okay? So what you will see is that there are what? Hydrogen here is seen, it seems as though hydrogen were coordinating with, has two bonds around it. So that's why we use dotted lines here, dotted lines to show that it is merely an attraction, an electrostatic force, an attraction due to what? Electrostatic force. Okay, so there is a partial negative, this is a partial positive, this is partially positive, this is partially negative, this is partially positive, partially negative, partially positive, partially positive, partially negative, partially positive, partially positive, partially negative, partially positive, partially positive, partially negative, partially positive. So these dotted lines that you are seeing here are mere attractions between the partial charges, the partial dipoles. Is that okay? So these dipoles here create an attraction between themselves, between each other. Is that okay? So there is hydrogen and oxygen. That hydrogen and oxygen has bonded here before, right? But this hydrogen will still seek to coordinate to this guy because it is highly electronegative. So take note that the substances that were engaged in hydrogen bonding, the atoms rather that were engaged in hydrogen bonding, must be highly electronegative. must have high electronegativity value. That is, the electronegativity value must be very much greater than hydrogen. So we commonly see nitrogen, which has a electronegativity value of 3.1. So if you compare that to that of hydrogen, which is 2.1, that is really great. That's 1.0 difference. Oxygen, which has a much more greater electronegativity value. Fluorine, which has a more electronegativity value also, and chlorine. And rarely do we see it with carbon. Very rarely, exactly. So, but the point is this, that this dipole-dipole interaction is what you call what? Hydrogen bonding. Exactly. The dipole-dipole interaction is what you call what? Hydrogen bonding. Okay, now, this electrostatic force between them is actually weak. Exactly, it's actually weak, but it has a lot to contribute with, organic compounds. It has a lot to, it affects their physical properties. It affects their physical properties. Okay, some of their physical properties. First, what organic compound or which organic compounds do we see this hydrogen bonding? We see them with alcohols. We see them with phenols. Okay, we see them with amines, okay, we see them with sugars, carbohydrates, alkanals, or aldehydes. So we see hydrogen bond. These are the organic compounds in which we see these guys, this hydrogen bonding, and this makes them slightly what? Polar. Is that okay? It induces polarization in them, and because they have slight polarization, it affects majorly two of their physical properties, which are what? Solubility and their boiling points. Okay, actually the physical properties that are affected are their ionization first, their ability to ionize, exactly, then their melting and boiling points, and melting points, which I'll be talking about, and it also affects their solubility in water. Does that make sense now? Solubility in water. Okay, we already know that organic compounds only dissolve in organic solvents such as ether, benzene, etc. But in this case, because these guys are polar due to hydrogen bond, then they are able to dissolve in water. All right, let's talk about their boiling points now. Let's talk about their boiling points. Now, you can understand that organic compounds that have nearly equal molecular weight, they are going to have almost the same boiling point, right? For example, in alkanes, you will know that the boiling point actually increases as you go down the group. The boiling point increases with the molecular weight. Okay, so for example, if we compare propane. Let's compare propane and ether, okay, in their boiling points. Now, propane has, this is the formula of propane, CH3. Okay, now what will be the molecular weight? 12, 12, 12, that is 36, 36 plus 3, 3, 6, 8. 36 plus 8, that's 44. So the molecular weight is 44. Then ether, let's use methoxymethane. Okay, the reason why I'm putting this is so that you can see the difference in their electronegativity values. Now this guy is going to be CC12 plus, that's 24 rather, plus 6, 30 plus oxygen, 16, 46. So the molecular weight of this guy is 46. Now, the observed boiling point of this guy is actually, negative 45 degrees Celsius. Negative 45 degrees Celsius. But the observed boiling point of this guy is actually negative 25 degrees Celsius. So you notice that the boiling point of this guy is quite higher. Now, relatively higher. It's not high, exactly, but it's relatively higher than this guy. Why is that? Because of what? Oxygen here that creates a sort of dipole. Now, there is no actual dipole here because the electronegativity difference, the electronegativity value of oxygen and hydrogen and carbon rather are not so much far apart. They are still far because once it's greater than 0.4, as I told you, it's far. Okay, but you cannot compare it to this where there is no dipole at all. Okay, so because of that, this one is very low, but this one is only relatively higher than it, but they are still close. Is that okay? And look at the molecular weights; they are very close. But compare that to, let's compare that to something like ethanol. Now look at ethanol. Ethanol is CH3 CH2OH. Okay? Now let's compare this guy with this guy. Now what's the molecular weight of this guy? It's going to be 2 carbons, 3 hydrogens. Okay, 46 also. Molecular weight is going to what? 46. Okay, by the time you compare this and this, you see that they have equal molecular weight. But look at the boiling point of this, is minus that. But the boiling point of this guy is observed to be about 78 degrees Celsius. Look at the huge difference in their boiling points. This huge difference is mostly due to the hydrogen bond that is, even though it is weak, I told you the hydrogen bond is weak, the electrostatic force is quite weak. But look at the huge difference in the boiling point of ethanol due to the presence of what? Hydrogen bonding. I hope that makes sense now. So that is it about the hydrogen bonding. So you see that, like I said, that the boiling point increases with more and more hydrogen bond. And the reason is this, that the electrostatic force adds more energy to the bond, gives the attraction between the molecules, makes the attraction make them more attracted to one another. Let's think of it that way. It makes them more attracted to one another. And so because of that, you need extra amount of energy to break the bonds of the ethanol for vaporization to occur. Do you understand now? So that is that about ethanol. Let's now talk about another property that is influenced, which is their solubility. Their solubility. Now, the solubility, because of the dipole that is induced upon them on organic compounds such as alcohols or phenols or amides, because of that polarization that is induced, then their solubility in water is possible. They become soluble in water. And what does that mean? It means that they will be able to interact with the molecules of water. So for example, let me show you how it will interact with water. So for example, we are going to have our ROH. So this is ethanol, this is alcohol. Okay, so this guy is going to interact with hydrogen, which is already bonded with oxygen and hydrogen. Does this make sense to you? Then this one will now interact with another O and H and R. Does this make sense? So this is alcohol. So when you put alcohol in water, this is what you have in summary. So I'm showing only 2 molecules of alcohol and 1 molecule of water. So 2 molecules of alcohol will be bonding with one molecule of water in that way, in that sequence, and that is how their interaction is. That's how the interaction takes place with them. So because of this hydrogen bond that is formed between them, there's what solubility. You know that this will be partially positive, partially negative, partially positive, partially negative. So the same way they are going to interact. The dipole will interact with one another, and then they will coordinate. So it will seem as though hydrogen were coordinating with 2 bonds. Okay, so and it is only under this condition that hydrogen behaves as though it were bivalent. Okay, so that's about solubility. Okay, so and the fact is that the solubility will actually decrease as you go down the sequence, the homologous series. That is, with the molecular weight, as the molecular weight increases, then solubility what? Decrease. So I said that what? Solubility decreases as molecular weight, not just molecular weight. Okay, but let's use that. Molecular weight generally increases. Okay, so what that means is that the more carbon molecules that you add to the chain. So for example, as we have ethanol here, to have ethanol has the solubility value of ethanol will be greater than the solubility value of propanol, which will be also greater than the solubility value of butanol, and like that, using primary alcohols as an example. Okay, so the solubility value decreases with more and more as you increase the molecular weight of the substance. Okay, then another thing you should also notice is that even though as the molecular weight increases, the solubility decreases. Now, there are some substances such as sugars, carbohydrates, aldehydes basically. Sugars have high solubility in water, and this is the reason. The reason is because of the many OH bonds that they have in them. Okay, so you have an example sugar as something like this. It's gonna have something like this. So I'm just drawing one, a trials. Let me draw a trials. So you can already see that there are many OH bonds here, right? Many OH bonds. If I continue to a hexose sugar like glucose, you're going to see that there are many more OHs, right? So because of that, there is high there are a lot of hydrogen bonding, which leads to the high solubility of that guy. But substances that contain carbon, hydrogen, sulfur, carbon, hydrogen, or halides, they do not dissolve appreciably in water, and that's because of the absence of hydrogen bond in them. So that will be it for this video. Do well to see the next video, which will be on polarity and the effect of polarization. God bless you. Subscribe to the channel as well and share the videos with your friends.